Hello and welcome to the third lecture for ECE 205. So let's jump right in it. So the lecture goal for this lecture is to focus on solving differential equations of this form here. So here, h of y is assumed to be a non-constant function, so that this differential equation here will be nonlinear. Okay, so before we get into the details of solving this, let's talk about this equation in terms of nomenclature that we've discussed in the previous lecture, introduce some new nomenclature, and then talk a little bit about some of the problems we might encounter when trying to solve differential equations of this form. So in terms of our previous nomenclature, just pause the video for a second and try to classify this differential equation. Okay, so 1 is going to be a nonlinear, so nonlinear coming from the fact that we have this term here, and h of y does depend on y in a non-trivial way. First order, because the highest derivative of y that we're taking is given by this term here. Differential equation that is homogeneous if and only if g of x is identically 0. So explicitly if this term here is 0. Okay. So further, differential equations that can be written in this form are going to be called separable differential equations. And the process of writing a separable equation into this form is called the separation of variables. Now, this concept of the separation of variables is a little bit more robust and abstract than just working with equations of this form, and we'll talk about that briefly when we talk about PDEs later in the course. Now, in the case where g of x is identically 0, there's kind of a natural solution that we can grab. So explicitly, if g of x is identically 0, then similar to in lecture 2, this function y of x is equal to 0 is going to be a solution to the homogeneous equation. Again, we're going to call this solution the trivial solution, and all other solutions are going to be called non-trivial. Now, in lecture 1, we built that nice method via the method of variation of parameters, where we first solved the homogeneous equation and used that solution to find solutions to the non-homogeneous version of the equation. Unlike first-order DEs, well, for linear first-order DEs, equation 1 might not have a general solution, and we often can't construct a solution to 1 from the complementary equation. Generally speaking, you often don't even try to do a method of parameters type thing for nonlinear equations. In some certain cases, it can help a little bit, but generally speaking, that's just not going to be the case here. We can, however, in sufficiently nice cases, find an implicit solution to 1. What do I mean by sufficiently nice cases? Well, generally speaking, we're going to want h and g to be integrable within a certain range, and for this course we're just going to assume that they're going to be continuous within certain ranges. But that will be more well-defined once we actually introduce a theorem later on in this lecture. Okay, next natural question, what do I mean by implicit solution? Well, I'll define that later as well. Okay, so let's explore this concept, and we'll start by looking into an example. Okay, so let's start with this example. Solve the differential equation y prime is equal to x parentheses 1 plus y squared close parentheses. So if you want, it could be a good idea to pause the video and try to solve this on your own, but there's going to be many other examples within this lecture, so if you want to see another example worked out, then you can just go ahead and watch the video without trying on your own. But if this was in class, I'd probably pause for 5 minutes to let you try to solve it. So let's consult Mr. Paint about how to do this. Okay, so there we go. Okay, so let's try to solve this. Well, what are our potential options maybe? So looking at this, we can very clearly see that this is a non-linear ODE because we have this y squared term here. So since it's non-linear, our techniques that we used in lecture 2 will not work here. Well, we could notice something kind of nice. Here, if I were to divide everything by this 1 plus y squared, then I would turn this differential equation into a differential equation of this form. Okay? So basically what we're going to do is apply separation of variables as our first step. So if we want to divide by something, we need to make sure that it's not going to be identically 0 in order to try to find a solution. Well, for any real value of y, 1 plus y squared is going to be strictly non-zero. Therefore, we can freely divide by this 1 plus y squared to separate variables here. So let's go ahead and do this. So we'll just get y prime, all divided by this 1 plus y squared. And this will simply be equal to x. So now we have everything that depends on y on one side of the equation, and everything on the other side of the equation depends on x, not y. So at this point, we can just do our trick that we did previously, where we just integrate both sides. So if we do this, on the left-hand side, that's just going to be the tangent inverse function. So here we just get our tan inverse of y. And on the other side, when we integrate this with respect to x, that will simply be x squared over 2 plus the constant c. So note again, I only put a constant on one side of the equation because we don't need to have two constants. Okay, so in this case, the next natural question is, can we isolate this to solve for y? Well, yeah, the tangent function is the inverse of arctan. Therefore, from here, we can solve this for y to actually get a nice general solution. In this case, that y is equal to tangent of x squared over 2 plus c. Just like that. So now, if I have a solution, it has to be of this form, because the way that I found this solution here was by simply manipulating the original equation algebraically. Further, if I have something of this form, if I take its derivative, you can quickly verify that it would satisfy this equation here. Therefore, this equation will be our general solution. So just a verification there. So now let's go back to the slides and continue going from here. Okay, so here's our solution in slide form, and if you want to see this kind of written out in Trench with a bit more explanation, you can just look at example 2.2.1 in Trench. Okay, before we continue, let's kind of analyze what we did to try to solve this equation and see if we can kind of generalize it a little bit. Okay, so in general, to attempt to try to solve a differential equation of this form, and here I say attempt to because we don't necessarily know if there's going to be solutions. And in general, for nonlinear differential equations, you can't always find the general solution. Well, to attempt to do this, what are we going to do? Well, if you notice previously, I ended up, once I had everything separated out, I just integrated both sides, right? So if I'm wanting to try to find a solution, there better be antiderivatives for these two functions here. So we first need to assume that there's antiderivatives of h and g such that the y derivative of capital H is equal to little h and the x derivative of capital G is equal to little g. If these antiderivatives do not exist, then we're kind of out of luck for that method that we used before, and generally speaking, solutions might not exist in those cases. This said, given that our functions our h of y and g of x are continuous on some intervals of consideration, then we know that antiderivatives will exist. So given that these are continuous somewhere, then we can find solutions. And you also want h of y to be non-zero. But yeah. Okay, so after we have this, we can assume that y of x solves the DE. So we're going to assume we have a solution and then try to find it. And then with this assumption, we can rewrite the differential equation using these antiderivatives. So how exactly can we do that? Well, here I have a little g and here I have a little h. I can replace those with g prime and h prime and see how this equation can be rewritten in terms of these capital G and h respectively. Well, capital G prime is equal to little g, so we can use that as a starting point. And now we know that y of x, or we're assuming that y of x solves the differential equation, so I can replace this g of x with h of y times y prime. Okay, so I can do this replacement here because I'm assuming I have a solution in order to try to find what that solution would potentially be. Okay, so now I want to replace this little h with capital H, and I can do this pretty straightforwardly just by a simple substitution here. So little h would just simply be capital H prime. And now here's where the magic happens for differential equations like this. Here, this thing is simply going to be the derivative of h of y. Why? Well, chain rule, right? If I want to differentiate this thing, I first take the derivative of h and evaluate that at y of x. And then since I'm differentiating this with respect to x, and y depends on x, I need to have this y prime of x term there. Okay, so the natural question is, how does this thing here help me? Well, this setup, this g prime of x is equal to the derivative of this thing, is basically what I used when finding the solution previously. To be explicit, this term here is my h prime of y times y prime, and this term over here is going to be my function of x. So what I did in this case is I just integrated both sides to find my solution, and that's precisely what we are going to do here. So in general, once we have something of this form, we can then integrate both sides. The integral of g of x, well, that's just going to be g of x plus c. I'm choosing to put the c here just for convenience. And on the other side, the integral of this, by the fundamental theorem of calculus, will simply be h of y of x. Okay, so kind of just putting all this together and looking at the big picture. Thus, for sufficiently nice functions, if there is a solution y of x to the differential equation, then equation 2 will have to hold. So here, what do I mean by sufficiently nice? Well, sufficiently nice in the sense that these equations, or these functions, have antiderivatives. And generally for this course, we're going to assume that they're continuous on some interval of interest. Further, it would be nice that if we can find a function y that satisfies this equation here, that function y would actually still be a solution to this original differential equation, right? Like that's the second thing we want for a general solution. So let's just notice something here. If we can find a function y that satisfies 2, then I can just differentiate both sides of the equation. And if I do that, I basically go from the line that I had here in step 3 up to the step 2 up here, right? So if I have a differential function that satisfies equation 2, then I can simply differentiate equation 2 to show that that function y also solves the original differential equation. Okay, so one thing that we want to be a little bit careful with here, I'm not saying that 2 is the solution to the differential equation. 2 is just an equation. The solution to the differential equation, if this exists and works out, is this function y. Okay, so since h of y could be something that we might not be able to solve for y, there could be lots of issues here, we don't have a general solution in this case, but instead, we call the function y of x in equation 2 an implicit solution to the differential equation. Sometimes you can isolate for y and get a function for y that is a general solution to the original differential equation, but sometimes you can't, and that's what we will be exploring in the rest of this lecture. Okay, so let's look at another example here. So solve the initial value problem, y prime is equal to negative x over y, both with the initial condition y of 1 is equal to 1, and the initial condition y of 1 is equal to 2. So here I'm really solving two initial value problems. Well, let's go over to Mr. Paint and work this problem out. So if I want to solve an initial value problem, a good first step is trying to solve the differential equation itself, because if I don't have a solution to the differential equation, how am I going to apply my initial conditions? So just looking at this, you can kind of tell pretty immediately, if I multiply both sides by y, I put this into a separable form. So I do my separation of variables and I multiply by y to simply write this as y times y prime is equal to minus x. So again, here I don't really have to worry about dividing by y or anything like that, since I'm just multiplying by y and that's not going to cause any issues with zeros. Okay, so from here I want to integrate both sides, so I'll just write this out a bit more formally than the previous one. So I integrate with y prime dx, and I integrate the other side with respect to x to get this integral here, dx. And now when I integrate this side, this is just going to be y squared over 2, right? The y prime dx, this whole thing here is just my dy, so that's kind of standard integral there. So from here, this implies directly that I'm going to get y squared over 2. And on the other side, here I'm going to get negative x squared over 2 plus my constant c. Okay, so now I can clean up this equation just by kind of noting that, hey, this is one of the standard forms for an ellipse, or circle in this case. So I can multiply everything by 2 and then pull this x squared to the other side. So if I do that, I'm just going to get y squared plus x squared is equal to 2 times c. So here my goal was to try to solve for y, right? So why did I just do this last step where I'm kind of unsolving for y? Well, in this implicit form here, we all know what circles look like, right? So by writing y as an implicit solution to the differential equation, we have this nice geometric meaning that we're all familiar of using with circles. Okay, so let's think about this constant term here, this 2c, for a second. Previously, with the different equations that we were looking at, c could take on any value we wanted it to be, right? Because it was an arbitrary constant, we could pick any value, and we still had a valid expression. Here, this sadly isn't the case. If c is negative, this would be a circle with negative radius. Well, yeah, that's kind of not a thing. And to kind of see why that would be a problem, if we just go back to looking at this equation for a second, if c is negative, then all this stuff here on this right-hand side is negative, right? So if I try to solve for y, there are no real solutions there. So if c is negative, I can't get a solution to this differential equation. So what I'm going to do is I can now say this factor 2c, I'm going to call it a squared, where a is some number that's greater than 0. So explicitly, I get this expression here. So just cleaning this up a little bit to give us some more room, that's the work for solving the differential equation. Now I want to apply these two different initial conditions, y of 1 is equal to 1 and y of 1 is equal to negative 2. Well, how would I do that with an implicit solution? Well, it's pretty straightforward. I just plug in 1 for all values of x. So here, just recall that this y is really just y of x. So here, when I go to use this first initial condition, here's what I get. Okay, and here I don't include the negative solution since I have that a is greater than 0. So now that I know what a is, I now want to plug this into this equation over here to find out what y is equal to for my solution. So in this case, I would simply get my y squared plus x squared is simply going to be equal to the square root of 2 squared, or just 2. Okay. And from here, for this case at least, I can solve this analytically for y, right? I could subtract off x, again, and then take the square root of both sides. So when I do that, do note that generally speaking, when you take the square root of something, you get the two roots, right? The positive root and the negative root. So does that mean there are two solutions, that the solution isn't unique? Well, in this case, no, because in my initial condition, I want y to be positive, right? So here I only need to take the positive root of this. So here I'm going to get 2 minus x squared. So this thing here in green will be my unique solution for this case. Okay, so now let's just notice something here. We had that concept of the interval of validity. What values of x can I plug into this solution? Can I plug in everything? Well, clearly not. I can't take the square root of a negative number to get a real solution. So from here, I need my 2 minus x squared to be greater than or equal to 0. Okay, so that's a pretty straightforward inequality to solve. So from here, I get that x needs to be bounded above and below by the square root of 2 for this to be a solution. Okay, so from this condition alone, is this sufficient for my interval of validity? Well, no. while this square root of 2 minus x squared is a valid expression for values of x between square root of 2 and negative square root of 2, the differential equation I started out with divides by y. Thus, I can't actually allow y to be equal to 0 to have a solution, right? So here I need to do an extra restriction where I need x to be strictly between negative root 2 and positive root 2. Okay, so when finding intervals of validity, do always keep this in mind, that just because you have a valid expression does not mean that the differential equation works for all those values. And here you kind of have another issue. This function isn't actually differentiable at negative root 2 or positive root 2 because of that singularity there. So that's another reason why you can't have the equals part here for this inequality. Okay, so that's solving this case for this particular initial condition up here. So let's clean that up by kind of shrinking it, putting it out of the way a little bit, and look at the other case. Okay, so here for this case, which I'm going to do in a different color, let's pick purple. So for this second problem, I basically repeat a lot of the stuff that I did before with a few small changes. So explicitly, applying my initial condition gives me the following for A. So now using this value of A in the solution that I found over here, just like I did previously, that simply gives me that y squared plus x squared, in this case, has to be equal to 5. Okay, so like before, I can solve this again, and when I go to solve this for y, I again get two roots, positive root and negative root. In this case, I have y is equal to negative 2, so in this case, I want y to be given by the negative root in this case. So I get negative 5 minus, root 5 minus x squared. Okay, so from here, I get the same type of constraint that I had before for my interval of validity. I need my 5 minus x squared. I need that to be strictly greater than 0. Again, strictly greater than 0 because I don't want to divide by 0 when I divide by y over here. And I also need my function be differentiable to even compute this y prime. So from here, this will strictly imply that my values of x will be bounded between negative root 5 and positive root 5. So here will be my interval of validity for this case. Okay, so what's the big picture here? Well, in this case, there were a few restrictions. The constants that I pick can't be any arbitrary constant in order to have a solution. They had to be positive numbers, right? Because in the case where they're exactly equal to 0, I just have a single point, so a circle with no radius, which is kind of problematic. And if my constants were allowed to be negative, then I get an even bigger issue where I have a circle with negative radius, which again is not a thing. So unlike what we saw in lecture 2, here our constants can't freely be anything that we want them to be. There's some restrictions that are put on these constants. Further, we don't actually have a general solution in this case, right? Sometimes I need to take the positive root, and in other times I need to take the negative root. And there is no nice, clean, well-defined way of picking which root that I want, other than defining y as a piecewise function that depends on y. While you can do that in this case, so just to show how you could define that real quick, we could say y is equal to the positive root, so explicitly a squared minus my x squared, when y itself is greater than 0, and the negative root when y squared minus x squared is less than 0. And in the case where y is 0, we don't have a solution, since in the original equation we divide by y. So you can do this. It's kind of messy. It's self-referential, right? Y depends on y. So it's not a function in kind of the standard sense of y of x type thing. And generally speaking, this isn't a good thing to do, but it is a thing. Just don't do it on homework. So since we can't really define a clean function of y of x is equal to blah, since there's these multiple branches, we don't have a general solution. Explicitly, we don't have a solution that can be written as a single family of curves. For this case, I need two. I need the positive branch and the negative branch. So no general solution, and not all the constants that you could possibly imagine plugging in can be plugged in. This can be quantized by a theorem, and let's do that now. Okay, so going back to the slides, here we have our solution in kind of text form. And if you want to see some of the details that I did in words but didn't put down when I wrote this down, look at example 2.2.2 in Trench. So now let's look at the existence of a solution. So again, sometimes we can't solve for y to find a general solution to this. And also sometimes we can't plug in certain values of c. So let's look at this theorem to quantify precisely when we can find certain solutions and what values of c are valid to use. Okay, so let's jump straight in. So it is worth mentioning before we get into the theorem that I have changed the wording a little bit of the theorem to make it a little bit more clear, at least in my opinion, and to clear up some ambiguity that the text has. Okay, so first, suppose that g as a function of x and h as a function of y are continuous on these two intervals respectively. Okay, so this is my starting assumption here, and it's actually easiest to visualize this theorem if I actually plot some stuff as we go along, so I will be doing that as well. Okay, so here, this g of x is defined for some particular x values, so let's just draw an xy plane, so this guy here, and kind of visualize what's really happening here. So here I have some point, say A sitting here, and I have some point, say B sitting here, and this is the interval upon which g of x is continuous. On the other side, I have this c here and this d over here, where my function h is continuous. So I'm really working within this little box roughly here. Okay, so I don't count the edges, so let's just delete those off a little bit. Okay, so my starting point is this open disk here, or open square here. Okay, so next up, let capital G and capital H be antiderivatives of G on the interval from A to B and H on the interval from C to D respectively. Okay, so we know these antiderivatives exist because G and H are continuous on a finite interval. So we know these functions exist by our statement that G and H are continuous. Okay, so next up, now I'm going to consider this subinterval, or this point within this region. So let x naught comma y naught be some point within this little region over here. So let's just indicate this here. So if I pick a point, and I will do it in green, I can pick some point over here. I don't necessarily know where it is, but this is just going to be some point x naught comma y naught that's inside this open box. And in particular, this is going to be a point such that h of y is not equal to 0. So why do I need h of y naught to not be equal to 0? Well, if this was exactly 0, then here I get 0 is equal to g of x, and I kind of have a degenerate equation at that point. So I need that h of y naught to not be equal to 0 at this point in order to make any progress going forward. Okay, so for this, I'm going to define the c tilde that in the text was called c, but I changed it to c tilde because this c is different than that c. So it's kind of an unfortunate choice of a variable name for the text. But I'm going to define this c tilde to be h of y naught minus g of x naught. So really what I'm doing is I have this open box. I have my functions g and h that are defined and continuous within the open box, and I have these antiderivatives that are defined within the open box, and I have this random point. So here all I'm doing is computing some antiderivatives, where it could be any arbitrary antiderivatives, g and h. And I'm just letting c tilde be the difference between those antiderivatives evaluated at that point. Okay, so do note that h is only defined with respect to y, it doesn't depend on x, and g is defined with respect to x and it doesn't depend on y. So here I'm just kind of using this point as a way of combining the information about h and g together. Okay, so if I have all of this set up, then there exists a function y, that's going to be a function of x, defined on some open subinterval a1, b1 of this bigger interval, such that some stuff is true. So let's first think about what the subinterval is in terms of our picture. Well, here I have my AB, and if this thing is going to be a subinterval of AB, then what I know is that A1 will be some point over here, and B1 could be some point over here. But in addition to this being a subinterval, I know that it's going to be a subinterval such that x0 is in this interval. So just doing it in kind of light blue, here I can pick my B1 to be any point between this green dot, so between that area for the green dot and over here. So if I just pick orange here, this could be where my B1 is, and this could be where my A1 is. Okay, so what I'm really doing is I'm taking this big interval, like this big open rectangle, and I'm going to kind of restrict it to a smaller open rectangle like such. Okay, so just drawing vertical lines here. The key thing of this theorem is I don't know what A1 or B1 is from the theorem. I need to actually potentially compute what they are based off of the particular solution to the differential equation and maybe the differential equation itself. Okay, so in addition to this point x0 being inside this open subinterval, I also have the property that y of x0 is equal to y0. So explicitly, this function y that I found, that's defined on this open interval, has the property that it satisfies some initial condition, y of x0 is equal to y0. And further, we have that h of y is equal to g of x plus the c tilde for all the x's within this interval. Okay, big deal. What does that tell me? Well, if I have a function y that's defined on this open interval with these properties that it satisfies this equation, then I know that that function y is going to be a solution to the original differential equation. That's nice. That's what I wanted. Further, I know that this function y satisfies this property here. Thus, if I put those together, y is therefore going to be a solution to the initial value problem here. So what this theorem is saying is if I have a nonlinear differential equation of this form, and I consider some point x0, y0, upon which h of y is not equal to 0, and if these functions h of y and g of x are continuous on some interval, so I have this little box here where I have continuity, then if I take these antiderivatives and pick any value of c such that this is true for that initial point for some antiderivative h and g, then there's a solution on this smaller subinterval here. So this interval from a1 to b1, that's going to be my interval of validity if I take a1 and b1 to be the smallest and largest values that I could choose respectively. Okay, so this is basically my existence of a solution theorem for nonlinear separable ODEs. Now notice that unlike with the linear ODEs that we considered in lectures 1 and 2, here my domain of validity could be smaller than the domain upon which these functions are continuous. And for any given initial point that I pick, that kind of is determining the interval of validity. So if I pick, say, this green point versus a light blue point over here, these could give me different domains of validity. They could overlap, they may not overlap, but yeah. So previously when I was talking about the difference between linear and nonlinear equations, where I said linear equations are kind of less interesting in some sense, this is what I mean by less interesting. With linear equations, we know lots of information freely, just kind of based off looking on the equation, but from nonlinear equations, we have a fair bit of work to do to understand what's happening with the solution. Further, I wanted to note two more things before we go on, and these things are mentioned in the text, but we can't arbitrarily pick the c tilde like we could with linear ODEs, right? Here, c tilde has to be a valid value such that there are these antiderivatives g and h, such that this expression is satisfied. Now really, this forced choice for C is kind of coming from the fact that you want it to satisfy the initial condition. So if I plug the initial condition into here and solve for C tilde for the solution, those are the only valid values of C tilde that I can use. So this proof really isn't this theorem really isn't a constructive theorem for how to compute C, but instead it is more just telling you that, hey, only these C tildes are valid. In second, which I noted this previously, this expression here is not the solution to the differential equation, but instead the function y that satisfies this equation is the solution to the original differential equation. Okay, so finally, I'm not going to actually prove this theorem. As stated in the text, this does require information that is beyond the scope of this class. And explicitly, we need to know a theorem about how to quantize parameterizations of level curves of some certain surfaces in terms of these implicit type expressions here. And I'll elaborate on that a little bit after we go through another example. So let's turn our attention to an example. Find all solutions to this equation here. So it's immediately obvious that this isn't of the current form of a separable equation, but if I divide by 1 minus y squared, then I can do separation of variables and have a differential equation in the standard form of a separable differential equation. But if I want to divide by this thing, then it needs to be the case that 1 minus y squared is not equal to 0 identically in the domain of interest. So from here, you can notice this really tells me that y, if I just solve this entire thing for y, can't be equal to plus or minus 1 identically. Okay? And further, if you plug in y is equal to plus or minus y into this, you get that the equation is satisfied. So we need to restrict our further consideration to the case where y is not one of these solutions. Okay? At the end of the problem, we'll try to take the solution that we find and recover these solutions, and we'll see if that's possible in this case. Do recall it was possible for the case of the linear ODEs. Okay, now further, since this is a continuous function, there's going to be some interval upon which this whole expression here is non-zero, given that we avoid positive 1 or negative 1 for y. So that means we can divide by this to get a new equation that we can then solve. So I'm also going to pull the 2 over just for convenience in one of the next interval steps. Okay, so from here with this assumption, with this thing being assumed, we can say that this differential equation can be transformed into 2y prime, all divided by this expression here, 1 minus y squared is equal to x. Okay, so now I know x is continuous and everywhere, so this bit's not going to be a problem. And this function over here, this 2 divided by 1 minus y squared, I know that's going to be continuous for some intervals, just basically any interval that avoids plus or minus 1. So I know there's going to be a solution to this differential equation, at least for some initial conditions. So I can now proceed knowing I'm going to find something and integrate each side of the equation. Okay, so direct computation to integrate this gives me, well, integrating this with respect to x, I'd want to evaluate 2 dy, all divided by 1 minus y squared. And on the other side, I want to simply evaluate the integral of x with respect to x. Well, that will simply be x squared over 2 plus some constant c. Okay, now I want to evaluate this integral. So let's do the work on the side to evaluate the integral. So first of all, I could pull out a negative, and that'll make things a little bit cleaner. I could rewrite this as negative 2y or dy all over y squared minus 1. So now, y squared minus 1, that simply is y plus 1 times y minus 1. So I'll do partial fraction decomposition. So partial fractions here. So to do partial fractions, just recall from here, I want to rewrite 2 divided by my y minus 1 times y plus 1 as a sum of these two terms. So some term that I don't know what it currently is, so let's just call it a divided by my y minus 1. And to this, I'll have a plus some b divided by y plus 1. So you all should be familiar with partial fractions, but just a kind of quick review, let's go through this here. So the natural thing to do is to multiply by this y squared minus 1 term, and that turns this into 2 is equal to a y plus 1 plus b y minus 1. Okay, now I can plug in any values of y that I want to try to solve for a and b. So let's just plug in negative 1 here. And if I do that, this term goes away. And if I plug in negative 1 here, I simply get 2 is equal to minus 2b. And if I solve that for b, I simply get b is equal to minus 1. Similarly, if I plug in 1 in for y in this case, let me just give myself more space. But if I plug in 1, I would simply get 2 is equal to, so here if I plug in 1 to this bit, I'm going to get 2a. If I plug in 1 here, I get 0. So that just gives me that a is equal to 1. Okay, so then I just take these coefficients, plug them into here, and then I simplify my integral. So this integral will simply be equal to negative the integral of 1, so positive from here, divided by y minus 1, plus negative 1, all divided by y plus 1, and this is all with respect to y. Okay, so let's remove this partial fraction work here. Pause the video now if you want to see it for a bit longer. Okay, so from here, we then want to evaluate this. Well, these are both just ln, right? So from here, I'm going to get negative. So here I'll have parentheses ln of the absolute value of y minus 1. Okay, and on the other side, I'm going to have a plus. So here I'll have negative from this little bit here, ln of the absolute value of y plus 1. And then, of course, we have a constant of integration, so plus some constant c, which we will promptly ignore because we already have the constant on the other side. So do keep in mind, like you could keep this plus c all the way through, but it's just going to make you have to do a bit more work, right? So it's kind of convenient to drop it here. Okay, so this can be directly simplified. So here, if I just expand out the negative, this is simply ln of this term with a positive in front of it, so y plus 1, minus, on this side, we'll have a ln of absolute value of y minus 1, and this simplifies simply to be ln of the absolute value of this divided by that. So this term here. Okay, so for your homework, I want to see kind of all this work sitting there. But for here, since we've done the scratch work on the side, I'm just going to replace this integral with that. Okay, so now if we can, it'd be nice to solve this whole thing for y, just so we have a nice clean solution, right? While we have an implicit solution here, having an explicit solution is much nicer. So let's take e of both sides and try to clean this up a little bit. So if I apply e to this side, I'm simply going to get the absolute value of this thing here is equal to e to this whole expression here. And then I can split that up by writing it as e to the c times e to this power. So let's just do that here real quick. So now it would be nice if I could drop the absolute value, and we know how to do that, right? We just want to take plus or minus of the other side. So from here, let's just drop the absolute value, and I can rewrite this as my y plus 1 over y minus 1 is equal to, let's just call this thing k times e to the x squared over 2, where k is going to either be plus or minus e to the c, depending on the sign of this term here. Okay, now I want to isolate this whole thing for y. Well, how can I do that? Well, I can multiply by 1 minus y to start with, and then I can combine all the terms for y. So let's do this kind of scratch work, and then I'll just solve for y in the final solution here. So giving myself some kind of space here. Here, multiplying by y minus 1 would simply give me this expression here. And then collecting like terms for y would give me this expression here. And then finally, I can divide by y to rewrite this as y is equal to this expression here divided by the other term. Okay, so I want you to notice this is actually a problem that's in the textbook, and I purposefully pulled the left this negative in here when I rewrote this term here to show you that you can get different solutions to the same, like different functional forms for solutions to the same differential equation. So if you look at this versus the solution in the text, they're slightly different in the fact that here I don't have e to the negative x squared over 2, and if I cleaned up these signs, I have a difference in signs between the two solutions. So just keep that in mind. Just because you get a different functional form than a solution that was, say, presented in one of the solution manuals, that does not mean that your solution is inherently incorrect. Okay, so let's clean this up and then analyze the solution a little bit. Okay, so if we wanted to verify that this was a solution, we could take this, take its first derivative and plug it into here, and we will see that it is in fact a solution. So if I take this and combine it with my other two solutions, I know that my three solutions are solution like this for valid values of k, which we'll talk about in a second, y is equal to 1, and y is equal to minus 1. Now, we know k can be plus or minus e to the c for any value of c, just from our work over here. And this tells us that k can be any number other than potentially 0, just from this. Let's check what happens if I plug in 0 in for k. Well, when I do that, so if k is equal to 0, I find, well, here I'm just going to get a 0, so this term will go away. And here I'm just going to get a 0, so this term will go away. And I just get negative 1 over 1. So if I allow k to be 0, I get the solution y is equal to minus 1. So really, the solution y is equal to minus 1 is contained in this closed form here if I relax the assumption that k is equal to 0. So what I can do is rewrite the solution as follows. But it's not possible to include this y is equal to 1 solution in this functional form that I have here. Because, I mean, quite frankly, there's no other real numbers for k that I can plug in. Now, notice this also differs from the text. In the text, they were able to get this y is equal to 1 solution, but not the y is equal to minus 1 solution in terms of their closed form formula. So this is also a standard thing that you will run into when solving nonlinear differential equations. Depending on your choice for doing simple things like leaving a negative on one side of the equation versus the other side of the equation, you will obtain better results around certain critical values, like in this case, the plus or minus 1. Okay, so that was a pretty nifty example. And again, look at example 2.2.5 entrenched to see another way that you can solve this to get a different functional form for your solution that allows you to capture one of the these singularities here that we weren't able to capture in our setup. Now, before we go on, I want to examine one thing in Trench. So here they actually plot the direction field for that example that we just considered. So here, within this direction field, you can kind of see there's these two regions, -1 and +1, like, yeah, positive, negative, where we have these constant solutions that correspond to the singularities that we found here, right? So, and around each one of these, kind of no matter which way you go about it, you can either encapsulate one of these into your functional form for your solution or the other, but not both. And kind of fundamentally, the reason why you can't get both of them is because in this functional form of the solution, you either have to divide by y minus 1 or y plus 1 once you integrate this out. And depending on which one you divide by, that's going to be the solution that you can't get. So we divided by y minus 1, thus we can't get the y is equal to 1 solution. In the solution of the text, they divide by the y plus 1, thus they can't get the y minus 1 solution in terms of their closed form. So that's something that's just kind of cool that I thought was worth noting here. And in general, there are no kind of hard, steadfast rules upon when you can get those type of solutions. Okay, so before we go on to our last couple of examples that we'll kind of go through relatively quickly because you've seen a few examples by now, let's give kind of a quick recap of what we've learned between lectures 1, 2, and 3. So the linear differential equation of this form, where p and f are continuous functions on some interval ab, always has a general solution. That was theorem 2.1.2a. To find that, we used the variation of parameters. And thus, the initial value problem here also has a solution for any initial point x within this range and any arbitrary value that you picked y naught. That was given by theorem 2.1.2b. Okay, the existence of a general solution that works for all values of c gives us the existence of a solution to the initial value problem. Now, if we turn our attention to nonlinear problems, in contrast, a general solution is not guaranteed to exist for nonlinear equations of this form, separable equations, even if h and g are continuous on a, b. Explicitly, we have some restrictions on the constants that you can plug into the general solution. Well, not general solution, but that you can plug into the solutions that you can find. And there can be solutions that you can't write in terms of one closed form, like we saw in the previous lecture slide. Further, in general, one can't actually even determine the interval of validity by simply examining the functions h of y and g of x, like we could in this previous case over here. Okay? In general, this will depend on your initial condition. Now, to demonstrate that this depends on your initial condition, let's go through this example real quick. Since we're out of time, if this were to be a traditional lecture, I will very quickly go through this case. The solution is given in Trent as well, so if you want to look at their solution as opposed to mine, that's perfectly valid. But let's just quickly go through it. Okay, so here, this could be separable if we divided everything through by y squared. So we're going to assume that y is not equal to 0 and divide by y squared. So if we do that, we simply get this expression here. And we now integrate with respect to x. We then solve for y. Now that we have this solution to this equation, we want to apply the initial condition. So here, if we go to apply the initial condition, we simply get this term here, which of course, solving for c simply gives us this. Now, if we take the thing that we have for c and plug that into our solution to get the particular solution, we find that this is the particular solution. So now the natural question is, what is the validity or the interval of validity of the solutions? Well, here we have to really consider what the initial condition is to determine the interval of validity. For instance, if y naught is equal to 0, then this term here vanishes, and you can plug in any value you want for x. So we have if y naught is equal to 0, then the interval of validity is all real numbers. Now, if y naught is less than 0, then this will be 1 plus some positive number times x squared, and that term could never be 0, right? So in the case where y naught is less than 0, we also have that the interval of validity is everything. So we can replace this equal to sign with a less than or equal to sign. Okay, and finally, if the y naught is strictly greater than 0, what is our interval of validity in that case? Well, we would want to know when this 1 minus y naught times x squared would be equal to 0. So pretty straightforward calculation off to the side gives us. Okay, and from here, we know my initial value of x was 0, so I know 0 has to be in my interval of validity. Therefore, my interval of validity will simply be this interval here. Okay, and again, I want this interval and not one of the complementary intervals because I need my initial condition to be in my interval of validity. So from here, it's pretty obvious that before I started this problem, I would not have guessed from this expression here that my interval of validity should change depending on what y naught is, or that it should be this particular interval here, right? And that's just kind of the nature of the beast with these nonlinear differential equations. Okay, so we'll just clean this up and throw it into the lecture slides. Okay, hopefully that's a little bit cleaner for reading off the lecture slides. Okay, so finally I want to look at one example, and this will be extremely brief. But say if we wanted to solve this differential equation, we actually have two options now. So let's look at Mr. Paint and discuss the options very briefly. Okay, so the first thing that we can note is that this is actually a linear ODE, right? So what we could do is we could apply the method of the variation of parameters. So we could do VOP, and we could solve this term here, plus y is equal to 0. We could solve this, and doing that, we would see that y would be exactly arbitrary constant times e to the negative x. Okay, and then what we would do is make our little ansatz. So we would say, hey, let u be an arbitrary function, and we're going to look for a solution of the form y is equal to u times e to the minus x. Again, just picking some value for the constant. We would take this ansatz, plug it into the equation, and we would find this equation that we would need to solve. And then we could solve this by dividing by this e to the negative x, and then just integrating. And that would simply give us this solution here. And then if I used this in my form over here, I would find that the solution, the general solution, would simply be y is equal to the e to the x, e to the negative x cancels to give me a 1. And then I would end up with just a plus c e to the minus x, where c could be any real number. Now, on the other hand, if I simply take this and subtract off the y and then assume that y is not equal to 1 and divide by it, I can turn this into a nonlinear differential equation. So to be explicit, I would have this is equal to 1 minus y, and then this would become. Now I could do my standard thing where I integrate both sides with respect to x and find my solution. So if I do that, this is what I find. And then from here, doing the standard trick with the absolute value, I would get. And this is the exact same solution that I had over here, just with a different choice in the constant. So if I were to give you this differential equation here in red to start with, it would be a good idea to potentially maybe multiply by this 1 minus y, and then just use the fact that we could do variation of parameters to solve this, or vice versa. You might find it solving it this way easier than doing variation of parameters. So just keep an eye out for that. It's a common thing that happens in differential equations, that there's multiple ways of solving a problem. Okay, so let's clean this up and make it look like a little bit nicer of a solution, and then post it in the slides. Okay, so here's just kind of a quick breakdown of the rough steps that you need to do for the two different methods, either if you assume it's linear and use variation of parameters, or if you treat it as separable and use separation of variables. Okay, I skipped a few steps here, but you should be fine kind of going through it. Okay, so let's talk about the assigned reading. So I want you to read section 2.2, and for practice, I want you to look at these questions. Again, don't look at all of them and fix the number there, but don't look at all of them, just pick a handful, try them. You can try some later, but on those pages. So I will leave you with a parting meme, general solution. Here's our nice linear equation, assuming those are continuous. Yeah, it exists. Over here, no, you can't have the general solution. Okay, so I wish you the best of a week and all that good stuff, and hopefully I'll see you around in office hours. If not, I will see you during the you'll see me during the next video.